Remember, electricity is dangerous. Always make sure you're properly trained before working with electricity and electrical equipment. Ever opened a control panel, stared at a ladder diagram, and thought, "What am I even looking at?" You're not alone. Ladder logic can look like a foreign language the first time you see it, but once you understand the basics, it's surprisingly simple. In this video, we'll take a simple electrical circuit and turn it into a ladder diagram. We'll explain what ladder logic is, how it looks when it's hardwired, and how it appears as a PLC program. By the end, you'll understand the connection between real circuits and ladder logic diagrams. Now, let's take a look at a simple electrical circuit. Here we have a DC power source, like a battery or a power supply, connected to lamp 1 through a fuse and a toggle switch. Now, if we close the switch, the lamp will turn on. This is what we call a control circuit because the switch controls the lamp. But notice, it's a manual control, since someone has to physically close the switch to turn the lamp on. Now, this is the same circuit, but it's drawn as a ladder diagram. It's called a ladder diagram because it looks like a ladder. In the same way, once we close the switch, the circuit is completed and the light turns on. The first thing on the ladder diagram is the power line on each side. In this example, we have 24 volts DC on one side and 0 volts DC on the other. The positive side of the DC supply is always shown on the left side and the negative side on the right side. Now, if the power supply was AC, like 120 volts AC, then the left side would be the hot side, and the right side would be the neutral. We normally ground the neutral to the panel for safety reasons. The second thing in a ladder diagram is the rung. That's where all the control elements are placed, like inputs and outputs. In this example, the switch is the input, and the light bulb is the output. Now, let's add another parallel branch to our original circuit. This means we'll connect another load beside the first one, not in series with it. This is the circuit with another parallel branch added. These are now two independent circuits, both powered by the same power source. What I mean by independent is that I can close switch 1 to turn on lamp 1, and lamp 2 stays off. In the same way, I can close switch 2 to turn on lamp 2, while lamp 1 stays off. And finally, I can close both switches to turn on both lamps at the same time, if I want to. Now, let's take a look at the same circuit shown as a ladder diagram. Here I am showing the same circuit as a ladder diagram. The second rung represents the lamp 2 circuit. Looking at the original circuit and the ladder diagram side by side, you quickly realize that the ladder diagram is a much cleaner and simpler way to view an electrical circuit. It makes it easier for electricians and engineers to analyze and troubleshoot control systems. Let's see how the same circuit looks when represented in a PLC ladder diagram. First, we need to connect switch 1 and switch 2 to the PLC inputs. In this example, switch 1 is connected to input 1, and switch 2 is connected to input 3. We also need to connect lamp 1 and lamp 2 to the PLC outputs. Here, lamp 1 is connected to output 1, and lamp 2 is connected to output 3. Keep in mind, the input and output numbers don't always line up in order. It all depends on how the wiring is arranged in the panel and how the PLC addresses are assigned. Now, in our PLC program, we show switch 1 as a normally open contact from input 01 and lamp 1 as a coil on output 01. This means that when input 1 turns on, it will energize output 1, turning on lamp 1. By the way, if you're new to electrical symbols, there's a link in the description where you can download a free reference sheet. You can also check out my video, Demystifying Electrical Symbols, a beginner's guide to ladder logic. In the same way, input 3 will energize output 3, which controls lamp 2. But how does the PLC actually work? The PLC's processor scans all the inputs to check the system's current state. It then runs through the program, usually a ladder diagram, to determine what actions to take. Based on these instructions, the outputs are updated. This entire process, known as scan time, happens incredibly fast, repeating in a continuous loop to ensure real-time control of the system. Therefore, when we close switch 1, the PLC immediately scans the input state and then updates output 1. In this case, Closing the switch will cause input 1 to turn on, which in turn energizes output 1, lighting lamp 1. Here, I just gave you a quick preview of manual control, simply turning a light on and off, to show how a ladder diagram works in relay logic or in a PLC. So now you might be wondering, what does a ladder diagram for automation actually look like? Remember, in the old days, we didn't have PLCs. All automation was done using relay logic. So here, I'm going to show you a simple automation built with relay logic and how it's represented by a ladder diagram, which is the foundation for understanding today's PLCs. I am going to show you how we automate the movement of the cylinder with just 3 switches and 1 relay. This is the ladder diagram for the box pusher. In line 2, switch A is manually closed. Therefore, the relay 1 is energized, initiating the cycle in line 3. The box proximity switch detects the presence of the box and closes, energizing the forward solenoid in line 4 as the cylinder begins to extend. The pusher moves away from the home proximity switch. Since the switch is normally closed, its contacts close. Once the cylinder fully extends, the normally closed box proximity switch activates, energizing the retract solenoid. Now, let's see this control circuit in action and watch how the automation actually works. And that's a quick look at how relay logic and ladder diagrams form the foundation of automation. If you found this helpful, don't forget to like and subscribe for more tips and tutorials on PLC programming, ladder logic, and electrical control systems.